My name is Per Christer Lund. I'm a Science and Technology Counselor at the Norwegian Embassy in Singapore, or Innovation Norway. Welcome to the 8th day of the Norway-Singapore Science Week. We have been we are into the second area. The first was sustainable urban development, and now we are looking at decarbonization. Yesterday, we talked quite a bit on carbon capture and utilization and storage. And on Friday, we were looking at energy efficiency in industry. Today, we are focusing on hydrogen value chain, the first part of this webinar, and specifically on maritime applications from about 4:30 or 9:30 Norway time. We move over to the second part of that with the more focus on the hydrogen value chain. I am recording this event for distribution later, and I'm also encouraging all participants to take active part in the discussions. You can do that by posting your questions or comments on the chat, or raise your hand, and the co-chairs will allow you to, or they may allow you to take the word. It's up to the co-chairs. And I'd like to introduce the two session chairs, Professor Siwa Chan from NTNU Fuel Cells and Hydrogen Technology, and Professor Bruno Pollet from the Norwegian University of Science and Technology, NTNU, Department of Energy and Process Engineering. And without much further ado, I'll leave the microphone over to the two professors. Thank you.
Okay, good afternoon, Singapore, and good morning, Norway. Ladies and gentlemen, this is S.H. Chan together with Professor Bruno Pollet. We are chairing the session TC-3A on hydrogen value chain, global markets, transport and storage, and downstream application. Today, we have 5 distinguished speakers. Each will give a maximum of 12 minutes of presentation. And at the end of all presentation, we will have some time for the Q&A. May I invite the first speaker, Mr. Andrew Bedford, Regional Director of KBR Consulting Singapore, to present the topic on hydrogen value chain opportunity in Singapore. Andrew, please.
Okay, thank you very much for the introduction, and also to Per Christer for the invitation to talk at this event. I will get cracking as I've only got 12 minutes. So let's save my bandwidth. Okay, so today I'm going to talk in general terms about the hydrogen value chain and how it could be implemented and brought to bear in Singapore. And just check you can see my screen okay?
Yes, we do, Andrew.
Okay, great, thank you. So I've just started with this picture just to show my opinion, maybe, of how things are progressing right now and over the next decade. This is a picture of the Easter Hat Parade in New York back in 1900. And you probably can't really see the picture, which is quite low resolution, but there's only one car in this picture. And then if I jump to the next slide, this is 10 years later. There was actually, and I doubt you can see it either, there's only one horse in this picture. So there's been a complete transformation. Tipping point's gone past, and so 10 years before this, the biggest problem in New York on the streets was actually horse manure, and then around this time, the biggest problem started to become the lack of paved roads in New York. So it feels a little bit like there's a transition underway right now of a similar scale and speed, possibly to electric vehicles, and also some hydrogen fuel cells. So Singapore, being Singapore, is planning very well for this stuff, and realizes it has to take action to meet its decarbonization targets, which is set for 2030, and then reduce as fast as possible to net zero by 2050 or thereafter. They've identified a number of ways they can do this, and it's going to be natural gas, solar, regional power grids, which they've made announcements about in the past week or so for International Energy Week, and also low carbon alternatives that hydrogen could well fit into. So hydrogen is not a new topic. It's obviously been around for a very long time and known about for a couple of hundred years, as well as electrolysis. So there's been a lot of hype in the past. There's been moments of hope when it hasn't quite taken off. Right now, it feels like it's different. Perhaps we're coming to the trough of disillusionment, as shown on this chart. And maybe because of technology really is driving this change, as well as social change, perhaps accelerated by the current COVID crisis. It feels like there's an acceleration and people are believing in the technology, seeing the economics could work at a specific point in future. Could be 2027, could be 2030. But there's also other geopolitical aspects around this as well. Some people see it as improved diversity of supply, which results in a more secure overall supply chain of energy sources. It's perhaps more reliable in some senses, as it relies on the weather, but that depends on your perspective. So I won't go through the history in detail, but Singapore has been mass-produced since around 1900-ish through electrolysis, and the first large-scale electrolyzers were in Norway, hydro-powered, and something that's really getting a lot of interest again and taking off. So it's been used to produce ammonia ever since the 1920s, 1930s, and space shuttles. KBR has its own team at the Kennedy Space Center, managing and designing parts of liquefied hydrogen facilities for the past few decades, and many lessons learned there as well. And it appears to be taking off again now. So large-scale manufacture of electrolyzers are being invested in. The technology is improving rapidly now. There's a lot of investment. And within Singapore, there's a number of potential applications. KBR has been working on the hydrogen feasibility study with NCCS, NRF, and others. I won't go into those details, but I'll talk in general terms today. But there's a number of downstream applications that could include power generation, city gas, mobility, and potentially bunker fuel as well, aviation fuel with fuel cells. So I'll sprint through this, but it looks like the supply growth going forward will increasingly be renewable. It's carbon free. The costs are becoming very competitive in most locations, especially where there's no grid. It's already the most economic way forward on the whole. And then a number of companies, as shown around the chart, and there's many others, have made announcements. Often they're IOCs, NOCs, as Petronas just announced last week, that they're going to go carbon neutral and carbon zero at certain points in the future. And BP and Shell have made major announcements along a similar vein. JX we're working with at the moment in Malaysia. They've got their own big plans for large-scale hydrogen production with CCS as well to supply Japan, but perhaps the surrounding region. And really how it works is, as I suspect most people on this call know, there's going to be many global potential sources of hydrogen. It could be where there's existing gas with CCS. So people are discussing low carbon gas these days. And for Singapore in particular, you could either bring that gas in as low carbon gas, or you could do CCS in Singapore. You could also potentially produce domestic sources of hydrogen from biogas, but that is rather limited, as Singapore has unique context as a city-state and limited land area. There's also potential for offshore concepts, as Keppel and Vopak and others are doing at the moment, sort of floating data centers and integration of hydrogen. And then the main issues that people are tackling at the moment is how you economically get renewable hydrogen, which is the big vision, sort of moving away from fossil fuels, bringing down the cost of that enough, and then economically transporting it from places like Australia or the Middle East, or North Africa, where the best renewable resources are. So not reliant on a specific gas field, for example, and using ammonia, MCH or LOHC, or compressed or liquefied hydrogen, and getting it to Singapore itself. Okay, so there's many colors of hydrogen, which I won't go into the details, but really there's also many colors of hydrogen, so turquoise, blue, purple. There's nuclear hydrogen production being planned. I don't expect that would really fit into the Singapore context unless there's a neighbor with that in the future. But yes, I think the vision is green at some point in the future, but it's very hard for it to compete at the moment. There's lots of predictions about the market and also potentials for methanol with carbon capture, or ammonia as a carrier for hydrogen, which could also be used directly for powering in coal power stations in Japan, which they're planning up to 20% in one of those coal power stations initially as a full-scale pilot with JERA, I think. And Mitsubishi and others have also already tested 30% co-firing of hydrogen in a combined cycle gas turbine. So that they would be able to bring in ammonia and use the waste heat from the turbine to crack that ammonia and mix, it'd be really HENG or hydrogen enriched natural gas, which would be injected into the gas turbine. The benefit for Japan would be reduced carbon emissions if it's from a green source or with carbon capture, and more diverse sources of energy. So I just put this up in the slides just to show the potential of somewhere like Australia. It's not too distant from Singapore, especially if you're on this side of Australia. And this isn't an exhaustive list. We've just gathered some examples from public sources and news articles to say what might be happening. There's very public examples from BP and Woodside and the Hazer Group and others, some of which might have potential to export. And I think that the difficulty will be finding those companies with the cash and the credibility to realize those visions. And there's some that look more likely. I'd say a BP or a Woodside-driven project is more likely. South Australia's had a lot of support, but any of those major hubs or hydrogen hubs, which is Australia and Singapore, are really thinking of supporting in future. That they could be the supply to Singapore itself, and the difficulty will be bringing that landed cost of hydrogen down low enough if it's from a green source. I borrowed this slide idea from Woodside, who showed the land area required to cover with renewables if they were to produce enough hydrogen to equal the energy value of their current LNG exports. And this really illustrates the challenge that we and everybody has. So they need about 250 gigawatts of solar across that area to produce that amount of energy. And I think every year there's about 10 to 20 gigawatts of solar production. So it would take 10 years to produce enough solar panels to cover that area alone. Current production, right, which is increasing rapidly, but not quite enough. So it will take a while to build up and go through this transition, which makes it more likely that the blue sources of hydrogen from gas, most likely, some people are looking at coal, with CCS are more likely to win out initially, really because they're cheaper, and the technologies for carbon capture, which we've been looking at in great detail, they're improving and coming down in costs. So there's people saying $30 a ton, which of CO2, which is very competitive when the European price of CO2 is, I think, is around $20 at the moment. So it's not far off being competitive. And Shell has recently announced their own hydrogen division of technologies, which they say is now competitive at that carbon price. So it feels like it's moving much faster than people realize, the CCS element here. And that will probably drive the transition and ensure that that requirement for gas continues for at least the next decade, just because the scale of this challenge of decarbonisation is so big. And then I've put this sort of process flow scheme in here as an example, whereas it's got ammonia, but it could actually be an MCH plant, which is Chiyoda's technology, or Spira, or it could be a methanol plant combined with CO2. Because any of these could be a carrier for hydrogen. So you'd have the renewables here with an electrolyzer, a water supply. It could be grid connected, which would help make life a lot easier in terms of the storage. But the challenge with renewables from a downstream process perspective is that you have to manage the variability, which means you have to increase the storage of hydrogen. which drives up the capex of this whole plant in the middle. And then the CCS part itself, the challenge is what do you do with the carbon capture? As often there are not off-takers or there are not storage facilities nearby. There are technologies out there like to do with pyrolysis and catalytic technologies that will capture that CO2 as graphite that are up and coming. And I think they are receiving a lot of interest right now from various players globally. But these carrier chemicals might help unlock the export supply chain, because liquefied hydrogen is currently very expensive, isn't so efficient, and there are a number of challenges around carrying hydrogen in liquefied form or compressed, for that matter. So this slide just talks about the challenges of developing the hydrogen supply chain and its power supply, the supply chain itself, establishing it, the logistics, the offtake, who are the off-takers is often a big challenge for those Australian projects, a number of which we've worked on at concept stage. They're all grappling with that problem. So the off-taker is one issue, that you need to make the projects bankable. And often it looks like you would need government support to get any of these projects off the ground. And a carbon tax would certainly help. So each of the carrier chemicals has their own pros and cons. Ammonia, methanol, MCH, and liquefied hydrogen, which I've touched on, but I'd say the advantage of the first two, so MCH and ammonia, is that you can often reuse existing infrastructure and vessels, whereas a liquefied hydrogen would require, on the whole, and this is all in general terms, it would require totally new infrastructure. So this would be, for the longer term, I suspect, as the volumes of hydrogen required across the supply chain and by the off-takers increase, at some point in future, the volumes become so large that it doesn't really become economic to move these liquids around. So you'd want to switch to liquefied hydrogen, but the point at which that happens is certainly up for debate. And yeah, there are certainly pros and cons around, but the other two as well. So we keep very much an open mind around these.
And Andrew, we're running a bit out of time. If you can come to your conclusion.
Yeah, sure. Let me just check which slides I've got left. Okay. So in Singapore itself, put it back in presentation mode. The challenge is, how do you apply and where do you apply hydrogen first? Which do you give support to in terms of an off-taker? Mobility is often the highest value sector to support, where you're most likely to make some money. But in Singapore, which is a unique sort of situation, there isn't a big mobility market. There is some heavy haul and bus fleets that might make sense in terms of business operation security, but for the mobility sector itself, cars make just as much sense to go electric, as the distances covered aren't so large. City gas here has town gas, which is 50% hydrogen already. That appears to be one of the easiest ways forward. But the bulk of demand for gas right now is power and industry. So I forget the exact percentage, but it's certainly the bulk of it, maybe 60%. So that's the one Singapore has to tackle in the long run. It's also where I'd say the least, it's where the least money can be made, because it's very competitive in this space. And I borrowed this picture from, I think, Professor Ho's slide last week at the Nordic conference, and they presented there were some ways forward from the NRF's perspective. So that they've said there's potential to blend hydrogen into CCGT, and looking at turbines, hydrogen fuel turbines. And there are potential in the other sectors, in particular marine, with hydrogen fuel cells and ammonia as a bunker fuel, or methanol, because most of the vessel manufacturers are looking at sort of tri-fuel vessel engines going forward over the next couple of years. They're starting trials, and heavy haul vehicles, like I just said. So yeah, that's a very brief summary of my perspective on the hydrogen supply chain for Singapore, and just thought I'd highlight a couple of announcements in the past, I think, few weeks, which is the MOU between Australia and Singapore. Hydrogen and the supply chain is one of the key areas mentioned in decarbonised energy supplies. and also the electric vehicle charging network, which really supports that view that EVs make a lot of sense for Singapore for the smaller vehicles in particular. Okay, that was my slides, thank you. So let me know if you have any questions later on.
Well, the Q&A will be later.
Sure. Yeah.
Okay, so good morning, everyone. Thank you very much, Andrew. Our next speaker is Noel Xian, who is serving at the moment as president of the Singapore Hydrogen and Fuel Cell Association. Thank you very much, and good morning.
Thank you, Bruno. Good morning, Norway. Good afternoon to everyone in Singapore. My name is Noel Xian. Can I just request for your help to run the slides through?
Yes, just hold on a second.
Thank you.
Then I will share my screen. And do you see it here?
There we go. Thank you.
So just let me, just tell me when to flip.
Sure. Okay, we'll go to the next slide.
Next slide. Yep.
Yeah. Okay. So just to give you some background to the Hydrogen and Fuel Cell Association of Singapore. The Singapore Fuel Cell community had its beginnings back in 2015 when a group of hydrogen and fuel cell enthusiasts pondered on the future for this industry. In the past 4 years, interest in hydrogen and fuel cells gathered momentum, with more individuals participating in events organized by the community. These events provided the opportunity to share on the latest trends and development on hydrogen and fuel cell technology by our international and local experts, and also opportunities to meet and collaborate. With the government's push for a forced switch in the energy mix, where hydrogen was identified as one of the possible alternative low carbon energy, we decided to formalize the association and became the Hydrogen and Fuel Cell Association of Singapore on 27 November 2019. And in doing so, it will signal our support for the Singapore's government push for hydrogen and fuel cell development and deployment, as well as provide credibility to our members when dealing with local and overseas associations and organizations. Some food for thought. The Singapore Fuel Cell Community was also coincidentally the name of the original community set up and funded by the Singapore government back in 2007. Prof Chan, one of our co-moderators, was also one of the pioneers who was part of this community. Next, please. Right, so the objectives of the Hydrogen and Fuel Cell Association in Singapore is to promote, encourage, and assist in hydrogen and fuel cell related activities, namely raising public awareness, develop best practices and standards, developing our workforce and skill sets, organizing of events for sharings and collaboration opportunities, support and participate in national, regional, or international events, and partnership with local or overseas organizations and entities. At this junction, we will also be very happy to announce that we have signed our first MOU with the Australian Hydrogen Council, and we are also going to partner with DMG Events for next year's Guest Tech 21. Next, please. Okay, so we've identified a couple of challenges here and opportunities for us to explore. In the first part, increasing our national energy resilience. I think this was already mentioned earlier by Minister Chan Chun Sing in his opening address at SEAL, and also by Andrew in his presentation earlier on. So looking at how can add the forced energy switch to consider green hydrogen and carbon capture, storage and utilization as part of our efforts to reduce, to increase our energy mix and resilience. Next, please. The second challenge is really looking at reducing Singapore's carbon emissions. So we have a target of reducing our carbon emission by 36% by 2030 from 2005 levels. But is there anything more that we can do? So we can explore opportunities in the built environment, for example, how we can improve building energy efficiency with co- or tri-gen systems. For example, this was also done by HDB in a small pilot where a small SC stationary generation system was actually used and then powered by natural gas. Late in the 2010s, fuel cell was also used as a backup for command centers for hospitals, namely Tan Tock Seng Hospital as well as Khoo Teck Puat Hospital, a 5 kilowatt fuel cell as a backup system. Recently, we've seen on-site production of green hydrogen by the SPTI, Singapore Power Training Institute. This is the first net zero energy building in Singapore powered by green hydrogen. And back then in 2018, a small group of us visited the Mercedes AMG in Stuttgart, where 100 kilowatt PAFC was used to generate power, capture the waste heat for absorption chiller, and also the use of low oxygenated air as a fire prevention system for their warehouse. This is an example of a trigen system that can be explored. And of course, in the mobility sector or transportation sector, looking at trials reduce the emission from the vehicles. This part of the electrification that pushed the government. So back in 2004, we actually had a couple of trials with Daimler AMG, and also in 2008 with BMW. In 2010, we also had the fuel cell bus that was developed by NTU and Tsinghua University for the Youth Olympic Games. And also recently participation from Temasek Poly and NTU in the Shell Eco Marathon Series, showcasing the fuel cell technology that was developed locally. For the maritime sector, I think what is important is we can explore port vehicles, converting port vehicles into fuel cell vehicles. For example, the picture here you see the Toyota fuel cell forklift that was demonstrated at the Taiyo Nippon Sanso Corporation Kawasaki factory when we visited them early this year. Okay, next. So availability of hydrogen. Currently now we have brown hydrogen produced as a form of industrial gas. And in Singapore, we are also renewable disadvantaged. So production of green hydrogen may be limited. So what are the opportunities that we can explore, considering improving the efficiency of electrolysis or SMR process, or even carbon capture, utilization, and storage for industrial use or storage. But moving forward, I think the direction is towards green hydrogen, and we are considering import from other countries, for example, Norway, Australia, Malaysia. Next. Okay, reducing the reliance on overseas supply. So we have very few locally developed solutions. However, we can take heart that we have a couple of local companies who have already taken the step towards commercialization. One of them is OneBerry. It's a local SME specializing in security and surveillance, providing island-wide stationary cameras that are powered by solar, as well as methanol fuel cells. And we also have Duralite Power, spin-off from Temasek Poly, manufacturing its own FC that was used for UAVs, very similar to Spectronic, which is also doing the same thing. And also we have Prof Chan and his team, where they have developed numerous patents on catalysts that's used for fuel cell and hydrogen generation and purification. And they have also collaborated with many international universities. So the question is, can we identify a niche area where Singapore is able to develop its expertise on, for example, membrane technology for fuel cell, as well as electrolysis, similar to what we did for the semicon industry. So if we are able to identify that niche area and build on that, that will put Singapore on the map again, not just a tiny red dot, but a big blue. Okay, next. Okay, acceptance of hydrogen. I think the general public perception is hydrogen is a dangerous gas. And they always make reference to the Hindenburg episode. And how does this so the question is really, how does this compare to petrol or diesel, which is already readily available next to your doorstep at refilling stations? So I think it's important that we also change the mindset of the public in preparation for hydrogen to come to our shores. How do we explain that hydrogen is used in many countries and as an energy carrier? Why did Singapore identify green hydrogen as part of its fourth switch? What are the advantages of using hydrogen and the various applications? How can we overcome the safety issues? And these outreach efforts could be carried out through our roadshows and incorporating this as part of the school sustainability curriculum. So in early this year, when we visited the Hydrogen Museum in Tokyo, they have rich information on hydrogen and its characteristics, and also demonstration showcase, as well as hands-on experiential learning to actually give the public a flavor of what hydrogen can do as they scale up for the hydrogen economy for the Tokyo Olympics. Next. Guidelines to support hydrogen application. Currently, the absence of standards makes it difficult to roll out our pilot trials. While we can always make references to international standards, but there's always a need to include Singapore's environmental conditions, for example, the densely populated urban settings, and how we can overcome these obstacles. So the opportunities is really looking at developing of standards and technical references. And the other key area is really how can we professionalize the industry and upskill the workforce? How can we develop courses, for example, basic and advanced modules with certification to raise the knowledge and skill sets of the industry? How can we also leverage on this to create job opportunities within the value chain? For example, workshops to service and maintain fuel cell mobility devices. Next.
1 minute, please.
Sure, that's the last one. So right here, just a quick snapshot of our ExCo. I'm very happy to have a committed group of members who are actually contributing their time pro bono to actually organize the webinar. We did a webinar just recently on 30th of October, and we hope that we can also identify more opportunities for us to get in touch with our members and to provide them with the opportunities to collaborate. So this is my last slide. Thank you very much, everyone.
Thank you
so much.
Our next speaker is Professor Bruno Pole from NTNU, Department of Energy and Process Engineering. He will make a presentation on hydrogen research in Norway. Bruno, please.
Yeah. If I can actually get that presentation going. My system is actually crashing, which is not great. That's a
Oh.
Yes. It's the Sod's law, as I call it, yeah? Okay. All right. Can you see this?
Yes.
Brilliant. Okay. Good afternoon, good morning, everyone. So my name is Bruno Pole. I'm going to give you a quick snapshot on what we do in Norway in terms of hydrogen research. First, I would like to give you a bit of a flavor on NTNU Team Hydrogen. We are actually the largest hydrogen R&D cluster in Norway, with over 40 professors looking at really the value chain of hydrogen fuel cell R&D. We have PhD students, research students, master students working with us. We actually tend to publish a lot, to patent a lot, and we are also open to international research collaboration and exchanges. We also run courses on hydrogen and fuel cells at bachelor and master's level. When it comes to really the value chain, we're pretty much looking at from nanomaterials, from the catalyst development and hydrogen storage materials to really system development and system integration. We also focus a lot on hydrogen safety. Professor Paltrinieri will talk about it a bit later on. And obviously the technical economics and life cycle analysis, which is very important for the full hydrogen really value chain. In Norway, we also focus on the maritime sector, and we will have two talks this afternoon, well, later on, by Professor Mehdi Zadeh and also by Tomas Tronstad from Hyon AS, who will be talking about hydrogen in maritime applications. When it comes to the infrastructure, which is very important, we have a quite large R&D hydrogen infrastructure dotted across the Norway, Oslo and Trondheim as well. So we're looking at high temperature fuel cells on electrolyzers, but also low temperature fuel cells on electrolyzer. And each really region or each really universities and entities have their own really R&D facilities. So SINTEF on this Norwegian Fuel Cell Hydrogen Center is split between the Institute for Energy Technology, NTNU, and SINTEF. we also have in Trondheim, for example, where I reside, where I work, we are focusing more on the alkaline and also acidic electrolyzers, and also fuel cells, so PEM and alkaline fuel cells. But also we're looking at direct method fuel cell for the portable applications, and we're also looking at Oslo, the solid oxide fuel cell and solid electrolyzer cells. We also are now in the process to extend that Norwegian Fuel Cell Center to accommodate as well the manufacturing capabilities, which is very important when you look at prototyping. So there's also other really infrastructure in place where we're looking at more into the, I would say, ex situ analysis, from spectroscopy to fundamental electrochemistry with for catalysis, for example. And we have been quite lucky to get really some very strong nanolab really funding or infrastructure to look at nanomaterials and really all the specifics around spectroscopy analysis. So hydrogen in Norway, really we have five, really the strategy is structured around five really themes: energy security and supply security, a fully integrated energy market, energy efficiency, decarbonization of the economy, and obviously a strong focus on research, innovation, and competitiveness. As you know, that's in Norway we're very blessed in terms of 98% of our electricity comes from really renewable energy sources, mainly from hydropower, which is actually good news, and the rest from wind and thermal power. And I will not mention oil and gas, obviously, as we are a big exporter of ONG. Really, we are also big ambitions. We want to reduce the emission by 50% by 2030. And we then want to reduce it by 95% against the 1990s figures. We have a focus on really two types of hydrogen. I call it the blue hydrogen, from natural gas, combined with carbon capture storage technologies that we are very strong at. And obviously, the green hydrogen, trying to capitalize on hydro energy, and linked to coupled with water electrolyzers. And also we have, Norway has want to increase taxes on CO2 emission by 5% every year until 2025. Okay, so as I said, two focus here is blue hydrogen on green hydrogen. And really it's pretty much quite understandable, because Norway, this is something which is not new. I mean, as was mentioned early on, that we have a really history in producing hydrogen, in fact, green hydrogen. And the first electrolyzers to be installed was at North Hydro, in the late 1920s with 100 megawatts. And now we moved on to bigger beasts, really large-scale electrolyzers for the production of ammonia, which is used for fertilizer. As a matter of fact, I'm sure you can go on LinkedIn and also on Noel Hydrogen, which is one of the largest electrolyzer manufacturer, who's actually signed an agreement with in Spain for a fertilizer company to have a 20 megawatt electrolyzer installed. There's a big focus here. So three big focus in terms of the hydrogen strategy in Norway, which basically will also involve R&D at low TRL, but also high TRL levels. So three sectors: the maritime sector, heavy transport, and industrial processes. So all this really is supported by the Research Council of Norway, Innovation Norway, and Enova. And we are talking really quite substantial amount of funding to do that. And in terms of really the Norwegian government, there's four objectives. Here is increasing the number of projects on hydrogen fuel cell, on hydrogen-based solution in Norway, contributing to the establishment of a comprehensive value chain for hydrogen in Norway, facilitating the use of hydrogen in different sectors, and ensuring also further technology development to reduce production costs. This is very important, that point here, number 4. And obviously the objective is to create more green jobs and facilitate the creation of new value creation. really, some key facts here, but I will actually distribute that, or maybe Chris can distribute that via on PDF here. But some really key facts: we actually produce about 220,000 tons of hydrogen, per year, which is actually mainly for the ammonia, really, and also methanol production. We are also at Mongstad site, which is one of Norway's largest industrial areas. It's been chosen as a preferred location for the country's first liquid hydrogen production plant for the maritime industry. And I think this is very important because that will kickstart, that will be the catalyst really of our hydrogen utilization and hydrogen production in Norway. And this is important to a different sector, not only for the maritime, but also for the automotive and stationary applications. So according to the Noel hydrogen company, if we really want to address this shortage of this energy or green energy or hydrogen production, we need about really 4,000 gigawatt of electrolyte, which is actually quite huge. So there's a lot of scope for new companies or new industries to really get their hands into that. So when we look at the green hydrogen, we're looking about 12 trillion by 2050, which is basically more or less 11 times of the value of the Norwegian government pension fund. In terms of the potential of green energy, from hydropower, about 200 terawatt hour, which is quite huge, really, when you think about it. So this is something to bear in mind. We are very blessed in terms of, as well, we have two major really big companies. One is Statkraft, which is Europe's largest generator of hydropower, wind power, and solar power, but also Noel Hydrogen, as I said earlier on, which is one of the top-notch and largest manufacturer of electrolyzers. So they are focused on alkaline electrolyzer, but also PEM water electrolyzers. And obviously, Equinor is also have quite a stake as well in this hydrogen really production, through natural gas and CCS. So now this is actually a map that Sintef and my team put together, who are the main players in Norway in terms of hydrogen, from really industry and to our research and education on others. It's quite actually substantial. I was quite actually, when we put that together, I was quite surprised, but happily surprised though. So in different companies there, or different research really institute, we are focusing on hydrogen, from basic research to really more developed R&D to higher TRL, with a focus on different sectors, which is great. I'll give you also quickly a quick snapshot, if I have the time, what we have in terms of ongoing research projects, or even project demonstrators. The ship FC project, which is basically the use of green ammonia in shipping. The zero emission small ships as well. The free CO2 project, which is basically a hydrogen fuel cell for the highway coast roads. There's a shift project that Professor Paltrinieri will talk about in more detail, which is sponsored by the Research Council of Norway. And you have also all the really research project, and not such a project, focus really on the maritime application. On this, I'm sure will be covered by Professor Mehdi Zadeh and also Tomas Tronstad later on today. So really, in terms of this, we are also developing with projects. We have projects in local Norwegian islands, for example. We have the ELIS project, which is funded by the EU Council, the European Union FCSJU, focusing really on producing hydrogen. The objective is to have 1 ton of hydrogen per day, which is basically generated from a 2.5 megawatt electrolyzers, and it's actually installed in a very remote village in Bedford, in Finnmark, and which is powered by wind energy, which is very interesting. I will not go through all this project. As I said, I will give you this as a PDF, but for those who want more really information, I have a special Word document on this, so please feel free to contact me. I can give you here quickly a short project here for the one which is funded by the EU, the European Union. It's called Channel, which is really pretty much looking at moving away from alkaline or water electrolyzers and PEM water electrolyzers, and it's called basically based on anion exchange membrane electrolysis. Okay, I think I've enough time here. There's one slide here just to say there's a very important program or project or center called MOSIS, Mobility Zero Emission Energy System, which is actually led by IFE, and it's an 8-year program, and we're looking at really anything around battery technology and hydrogen, from materials to systems integrations. One of my last slide. My last slide here. So just to give you actually a bit of some recent news, we have had some quite some good news in the sector in Norway, and so a lot of investment coming on. Really, very recently, the Statkraft has entered into a letter of intent with Noel to develop actually really electrolysis plant to produce green steel at a place in Norway. I would like to thank you for your time, and if you have any questions, please send me an email. And thank you very much.
Thank you, Bruno. Would you like to chair the next one? Okay, let me do it. All right. Our next speaker is Dr. Lo Xiangjun, Executive Director of the A-STAR, Institute of Material Research and Engineering. And today's his topics of presentation is hydrogen research at A-STAR, include the catalysis, material science, and carbon utilization. Dr. Lo, please.
Hi, good afternoon, everybody. I'm trying to share my slide. It seems a little bit stuck here. Oh dear. Can you see the slides actually?
Yes,
we can see the slide called synthesis.
At slide 6.
Yes,
Yeah,
correct.
6.
That's a problem. I can't move. Yeah, I can't move anything. Hang on. Let me.
Well, don't trust fully the technology.
I think so, yeah. Let me just restart again. Apologies for this.
It's strange because it happened to me too as well. It just got stuck for some reason.
I have the same problem with Teams.
The same here, actually. It's not the first time.
Yeah.
Okay, yeah, look good now.
Look good, huh? Okay,
Yeah.
good. Oh, it's my first. I just press the slideshow. Or can I trouble someone to? Oh, it's okay. Yeah. All right.
Yep.
Good. Now, good afternoon, everybody. And I would like to just give a very brief presentation on hydrogen research at A-STAR. And this actually covers catalysis, the material science, as well as the carbon utilization aspects. And I'd like to first of all give credit to the main scientist who is working on this topic. His name is Dr. Liu. Dr. Liu Zhaolin is actually a senior scientist located in IMRI A-STAR, and his research is actually on electrocatalysis, energy storage systems, fuel cells. I'll talk a lot more about the work he did on fuel cells a little bit later. He's quite well recognized, and recently he's also pioneered the layered structured cathode material in a lithium-ion battery, as well as working on the microwave-assisted synthesis of the nanoparticle types of catalysts. These are usually for fuel cell applications, and also developing the catalyst, the oxygen cathode catalyst for rechargeable metal air batteries. He's actually quite well known in the field, and has been a recipient of awards, as well as done quite a few of industry projects with companies. Now, when we think about fuel cell, really the working principle of it is just using hydrogen and oxygen to generate electricity with a byproduct of water. So on paper, it looks like a very benign process. And actually this reaction takes place via what we call a redox reaction. So it's reduction and oxidation types of reaction. And when you look at the figure on the left-hand side, you can tell that this cell can be miniaturized, can be turned into a portable electricity source, and if coupled with the renewable energies, you can actually reduce the carbon footprint. But of course, the key challenges remain in the area of fuel cells, and one of it is how do we achieve excellent performance as well as long-term reliability at very low catalyst loading. Now we want to have long-term reliability so that the lifetime of the fuel cell will be able to pay for its own application. We also want to use as little of these precious metal catalysts as possible so that it can be more cost effective. Of course, we can talk about high performance, but usually at high catalyst loading, it does not make a lot of economic sense. So for fuel cell catalysts, actually the critical issue is on how do we tune the particle size, how do we control the shape? So shape matters. We could design the shape of the nanoparticle to have extra surface areas in contact. And what is the composition? Can we alloy this thing and we can make a better performance? When we're talking about the PT catalyst, actually the main problem is that your carbon monoxide will bind tightly to the PT surface and then it'll block the active site. And for the other types of bimetallic catalysts, there are bifunctional mechanisms where one portion allows you to do hydrogen oxidation or the oxygen reduction, and the other side will actually provide for the oxidation of your carbon monoxide, which is absorbed onto the sites. So at Institute of Materials Research and Engineering, we have actually done quite a lot of fundamental research in this area, and we do have a good idea of how such catalyst works. And a lot of this work has been championed by Professor Chan Siu Hua, who is a pioneer in this field in Singapore. And he has done a lot of this work through the fuel cell program that started in that was around 2007 and 2009. And this actually, in the initial days, had the EDB's involvement as well as Rolls-Royce investment into solid oxide fuel cell development. And this is not a one institute type of work. It is actually involving our various sister institutions such as ICES, the Institute of Chemical and Engineering Sciences, IHPC, our High Performance Computing Institute, and SIMTech, our Manufacturing Institute. And the objective that time was to build core capabilities in fuel cell technology, as well as to work with the industries, the companies such as Rolls-Royce through joint R&D collaboration. The solid oxide fuel cell, or the SOFC, as well as the polymer electrolyte fuel cell, they are externally funded projects. So through the Rolls-Royce as well as with the defense science organizations. And really, we are looking at three core areas: catalyst synthesis, membrane, as well as the fabrication of devices. In the area of catalyst synthesis, where we spent a lot of effort on at that time and still even now, we're trying to develop very highly dispersed nanoparticles on carbon. And this is actually a form of catalyst which is by now quite well established in this world. But if you look at our papers, actually we started looking into this as early as 2002. And we're trying to accelerate the reduction of the metal precursor and the nucleation of the metal cluster. So how do we design smaller particle sizes? And this really has to go hand in hand with the characterization tools that we have. And we are currently also working on having state-of-the-art transmission electron microscopy techniques to try to characterize and understand better how such catalysts work. We also want to create uniform temperature and concentration such that, for these nanoparticles, they can grow evenly and you get very consistent performance. And even then, in the early days, we have managed to outperform in terms of the current density over the commercial catalysts. Then later work, we're focused on using nano-sized colloids as precursors. Some images are seen here. They are very well dispersed, and the particles, they have a very fixed size. This is good for consistency in the performance. And we have also got the highly dispersed catalyst by polyalcohol reduction of the organometallic catalysis precursors. Then we also do work on electrocatalysts for hydrogen evolution reactions. The cobalt phosphides here, they are actually used for hydrogen evolution reaction in an acidic medium. And we have actually obtained various forms which show very good current density under both the acidic and the alkaline conditions. And these types of works is actually due to the high content of the cobalt phosphates and also the large surface areas that lead to high density of electrochemically accessible areas. So these types of considerations are important when we are developing catalysts for fuel cells. Next, the other portion that is very important is actually the membrane part. Now, when we think about a membrane, we usually have different types of membrane. There's ceramic membranes and there's also polymeric membranes. So the one that we are working on is actually a perfluorosulfonic acid and metal oxide type of membranes, or the oligomeric polyphenylene diazoxide type of hybrid membrane. So it's an organic, inorganic type of hybrid membrane. And this sort of proton exchange composite membrane has high stability and also higher lifetime. The proton exchange polymer comes together, intertwined with the ionomer that's crafted with the iron oxide, metal oxide nanoparticles. And we do see actually very good improvement in the performance under dehydrating conditions versus the native proton exchange polymer. And this is all because the material itself is held in place using the silica particles that have the ionomer that's grafted onto the surface. And finally, after working on the catalyst and the membrane, we want to package everything in the form of a device. Now, this is where the challenge comes in, because where you look at the structure of the electrode, you have to think about things like carbon paper, a diffusion layer, a catalyst layer, and of course the electrolyte. And then how we pack these things together in a confined space. And this involves a combination of the membranes. You do have to do the membrane electrode assembly as well as the PEM-FC assembly. And then this gives you, a very modest 1 kilowatt membrane stack. And such fuel cell devices, we did very, very simple proof of concept demonstrations in the past, mini fuel cells that can power things like radios, hybrid membranes. And right now we are actually working
Sorry, 1 minute left, please.
Okay, sure. And we're working on actually larger cell batteries with higher power capacities. And of course, we look forward to more types of collaborations with partners around. So just right, I've come to the last slide. And over here, just like to acknowledge support from A-Star, as well as SD Kinetics, and as well as DSTA. And of course, thank you everybody for your attention today. Thank you.
Thank you, Xiangjun. The next speaker, or our last speaker, is Professor Nicola from a Norwegian University of Science and Technology. He will speak to you on hydrogen safety and materials integrity for compressed hydrogen, liquid hydrogen, and ammonia. Nicola, please.
Nicola should have a video.
Can you play the video, please?
Per was supposed to play the video because my internet is not very reliable. I will play the video, hoping that my internet will work well then.
Do you want me to show it from my computer, Nicola?
Yeah, that was the agreement.
Yeah.
It might be good to use your, the video at your end.
I think if Per Christer can play it from your end, will be better, perhaps.
Yeah, this is the presentation, huh?
Yeah, it should be video.
Video.
Oh, the video. Sorry. I have this one only.
You want me to try mine?
Yes, can you do that?
Let me. Can you exit and try mine?
Yeah, I will. Sorry, I will do that. Yeah, try now.
Can you see that, the video?
It's
Yeah, can you double click on it? I see.
Prof. Xian, you have to double click on it.
Double click.
Yeah, just to
Yeah.
start the video. Just double
Stop
click.
video there.
No. Just double click on the file name to just start it.
Start already at my end.
Is it?
Yes.
Then I can just give the presentation without.
How about now?
I thought this would have been a solution against technical problems, but created more technical problems than what was supposed to.
I tell you what. Why don't you
Start.
Per Christer, why don't you actually open the presentation of Nicola, and Nicola can just talk. Yeah.
Yeah, sure. I can do that. And then we go like this. Yeah.
Okay. Good morning or good afternoon. No problem. Yes. Good morning or good afternoon, everybody. My name is Nicola Paltrinieri. The presentation will be focusing mainly on hydrogen safety and materials integrity. Given the short time available, I decided to disregard the ammonia part. Please proceed.
Let's see. There we go.
I started the presentation by showing a big European project in which I was involved a few years ago, named IntegRisk, about early recognition, monitoring, and integrated management of emerging new technology-related risks. It was specifically about emerging risks, okay? So this was to address the topic of, or at least to address the technology of hydrogen-related technology, and to mention the fact that we are in front of an emerging technology, given the growing number of applications and the growing volumes handled. But are we in front of an emerging risk associated to this technology? Well, if we look at the definition given by this big European project of a few years ago, we are also probably in front of emerging risks because we have new processes, new technologies, new ways of working associated to hydrogen technologies, which means we have an increased likelihood of exposure of the people that are involved in this technology. Please. Addressing the safety aspects of a technology in general can be considered as an enabler for this technology. In fact, and I'm again citing the IntegRisk project.
I'm sorry, there was a mistake here.
Lack of acceptance can kill even the best and the most advanced technology. Okay, and in fact, if Norway and Singapore are aiming to be world-leading technology-based societies, they need to address these safety assurance, and they need to provide a clear, responsible, and transparent insurance of safety associated to these technologies. Please. And I want to mention the accident that we had here in Norway at the hydrogen station in Kjøbe, in Sandvika, in June last year. UNOX is the provider, the company that was managing this hydrogen station. And as soon as we had the accident, UNOX closed all the stations in Norway and created a safety zone around the station. So the question is, was it necessary to close all the hydrogen stations in Norway? And was the safety distance created enough for this kind of scenario? Please proceed. Probably there has been a way to ensure safety in a transparent way, but also a way to provide to support, let's say, convince the stakeholders that hydrogen was managed in an appropriate way. So the closing of all the hydrogen stations in Norway has been also in the perspective of making the stakeholders aware that things are being handled as transparent, as safe as possible. But hydrogen, we can say that is not necessarily less safe than other fuels. Okay, the thing is, we need to put in practice the right safety measures to control this hydrogen. The characteristics of hydrogen, of course, are different from other substances, from, for example, hydrocarbons. So the problem in this case is, are the practitioners aware of the potential related accident scenarios related to hydrogen and hydrogen technologies? Because for sure, experts like me and you are aware of the some peculiar characteristics of hydrogen, but all the practitioners, all the operators that are handling hydrogen every day, are they fully aware of this? Please proceed. For instance, we have a scenario called boiling liquid expanding vaporal explosion. That is a scenario involving a physical explosion of liquefied hydrogen, in this case, that is usually stored cryogenically. In case of, for example, an increased heat exchange with the environment, we might have an increased evaporation of hydrogen inside the tank, an increased pressure inside the tank that might lead to a catastrophic rupture of the tank. This leads to a sudden evaporation of hydrogen. This evaporation would lead to this physical explosion, to this overpressure given by the sudden increase in volume by the liquid hydrogen. Another example of accident scenarios that might be considered as, I would say, atypical for hydrogen is this next slide. The RPT, the rapid phase transition. Also in this case, we might have a physical explosion, which means an overpressure given by the sudden evaporation of hydrogen. In this case, is more like liquid hydrogen leaked on a substance like, for example, water, see here in the picture, that increases the heat exchange between the two substances and might lead to an early rapid phase transition or a delayed rapid phase transition. Once again, this phase transition, so this transition from the liquid state to the gas state, might lead to an overpressure, so an increase of volume and then an overpressure. Of course, there can always be an ignition as well, since we have highly flammable substance involved that can lead to fire, flash fires, or vapor cloud explosions. Next slides, please. The problem of these two accident scenarios is that even the experts are not fully sure whether they are going to occur or what are the actual conditions for occurring, because there is quite experience on hydrocarbons related to these accident scenarios, but for hydrogen there is little experience on this. For this reason, we are running a national project called SHIFT, Safe Hydrogen Fuel Handling and Use for Efficient Implementation, that is studying these accident scenarios, that is going to run some experimental tests and validate some modeling that we have already performed. Next, please. Now, we have focused in these slides so far on the right-hand part of these current slides. So you see the release that may lead to an explosion, may affect the operator. So we have mainly focused on modeling what happens once there is a release of hydrogen and how then we can mitigate it. Because of course, modeling what happens after release of hydrogen means that we want to understand what is going to happen and we want to put in practice some effective safety measures. But what is also very important is the prevention, as you may guess. Prevention of this loss of containment, loss of integrity of the materials that are used for the containment of hydrogen, for instance. And for the interaction between materials and hydrogen, there are once again particular behaviors or mechanisms that are worth to be considered. Next slide, please. Example, there are very consolidated standards on inspection and maintenance planning based on risk. So the idea is I assess the risk in my system, I predict a risk trend for the future. Once the risk reach an inspection target, I will run an inspection in order to understand whether I overestimated the risk, and this is quite common because there are uncertainties, so we tend to be conservative to overestimate the risk, or maybe I confirm the fact that the risk was as predicted and I apply some maintenance in order to lower the risk. Next slide, please. The problem is that these approaches are relying on some degradation mechanisms of the materials used that are not specifically for hydrogen, of course. So these damage factors that you might see here in the middle in the figure, that you might have seen better in my video because I was circling them with my pen, are not fully describing the hydrogen attack, blistering, metal hydride formation, so the material degradation given by this interaction with hydrogen, which means, thank you, that we have more uncertainty in this evaluation of risk. So we are even more overestimating risk, and we might then need to run more frequent inspections in our system. Next, please. So we have seen that it's very important to have a good understanding of what are the materials behavior in contact with hydrogen, so how material sciences may help in the safety evaluation for hydrogen technologies. But what we also need to know is to support other type of operations, not only inspection and maintenance, for example, emergency planning. We have little operational experience on hydrogen, so we might need to rely on advanced techniques for training our operators, like simulations, like serious gains, and examples like you see in this slide. Next, please. To conclude, safety assessment should be considered as an enabler for hydrogen technologies. We have knowledge, we experts on the hydrogen characteristics and how hydrogen is behaving in these accident scenarios, but are the operators, are the practitioners aware of this? Especially if we look at the consequence analysis, so the accident scenarios that may occur after release or the materials integrity, there are some mechanisms that are not fully considered by standards or by current operations by practitioners. So we need to increase our knowledge on this in order to fully make these technology, to fully make these technologies grow, okay? And of course, we need to train the operators in order to be able to both operate these hydrogen technologies and react in case of emergency in an appropriate way. Thank you. The next slide is my contacts. I will be also happy to share these slides as a PDF because I don't know if you've noticed, there are some hyperlinks leading to publications and websites of research projects that in which I'm currently involved with my group in the Department of Mechanical and Industrial Engineering. Thank you.
Thank you, Nicola. The floor is now open for Q&A. You may send in your question using chat. First state your name and organization, then followed by your question. Well, there's no question so far. May I ask the first questions? I'd like to raise a question for Andrew regarding the hydrogen value chain opportunity in Singapore. May I have your opinions? What are the most challenging issues yet to be tackled in order to seize this opportunity? Andrew?
Yeah, sure. I'd say there's many challenges, but the first one is the lack of a market. Right now, there's a limited demand for hydrogen. You need the off-takers to use it, and to build up that market for the off-takers, you probably need some sort of government support in terms of financial subsidy or tax support, like carbon taxes. And you need to develop something like the power sector or industry. There's already captive hydrogen in Singapore itself for much of the industry. So it may be easier to start by introducing green hydrogen into one of those facilities or to the hydrogen network on Jurong Island, or a trial or a demonstration power plant, just to start building out that supply chain. It is not easy, and people are looking at various ways of building out that supply chain to help drive down the costs quicker. And it may be to use gas and produce hydrogen here locally for things like mobility hubs and heavy haulage, just to start off, and then gradually over time transition to the more expensive, at the moment, green hydrogen imported from elsewhere.
Thank you. Thanks, Andrew.
Okay.
More questions?
Yeah. Yes, thank you. I'd like to ask a question to Noel Chin, who is now representing, the organization is representing 150 companies. Could you say a bit more what kind of companies they are? That's a huge number, even compared to the overview from Professor Pollet of Norwegian stakeholders in the hydrogen space. That was less than 150. Could you tell us a little bit of the span of these companies, Noel?
Okay, right. Okay, thanks, Per. Okay, just update. I'm told that the membership has gone up to 200. And right now the membership is actually on individual basis. So these are individual members. We're not counting corporate membership at the moment. And they span across the academia. So you have the IHLs, you have the research institutes. We also have industry players from the hydrogen value chain. We have building owners as well, and as well as representatives from our public sector agencies. So I think we also have members from other associations as well joining us. Right now, why is the membership so high? Firstly, because of as I mentioned earlier on, because of the number of the work that we're doing that's aligned with what the Singapore government is trying to do. And I think the other one, again, because I always believe that until we have a successful demonstration of a hydrogen fuel cell application, we will still allow members to join us without any registration fees. So right now it's FOC. But until then, I think we need to also take stock of some of the costs involved in running the association. For example, how do we maintain our emails? How do we also organize events when safety distancing measures are being relaxed for us to do face-to-face interaction? And so I think right now we are looking at a sponsorship program, and these details will be released very soon. And we're also looking at other ways to actually fund our operations, likely by exploring the lead funding under Enterprise Singapore.
Thank you. I think Professor Paulet, you raised your hand.
Yes, thank you very much, Noel. Actually, it would be quite nice if I were to put you in contact with the Norwegian Hydrogen Forum, which is basically your equivalent in Singapore. I'm not too sure how many members we have, but I think it would be nice actually perhaps to link up with the president of our NHF, and perhaps we can I can actually send you an email and we can move that forward if you are interested.
Yes, we have Knut Linnerud here. I think you're still here. Can you say a little bit about the Norwegian equivalent, Knut? If you can hear me. No, okay. I just saw his name was there.
Yeah, me too. I did see actually.
Yeah, he is there. Okay.
Yeah, that's right. That's right. We'll be in touch with Miss Ingeborg. I think is that right, Ingeborg?
That's correct. Yeah. This is correct.
That's right. Yes, yes. So we'll be in touch with her. We've already got her email. So we'll explore how we can work with them together. Probably also see if we can also explore MOU and see how we can partner in this area. Definitely.
Excellent. Excellent.
Okay, I have one question for Dr. Loh Xiangjun. Can you share with us what research A-Star has planned on hydrogen and the fuel cell that would allow a collaboration with IHLs within Singapore and overseas? For example, our partners in Norway.
Was it a question for me, this?
It was to Dr. Loh.
Dr. Loh, Dr. Loh.
From A-Star.
A-Star, yes. Are you there, Dr. Loh?
I think he may have, he's not on the list, he may have dropped out. Did he?
Okay then.
Okay.
Then I would like to change my question and would like to direct it to Nicola. My question is, safety has been a paramount concern by the stakeholders. In your opinion, how long it will take for a society to accept and adopt hydrogen at residential areas? The issue is, if a fuel cell vehicle can carry 4 to 6 kilograms of hydrogen at high pressure and driving around in a crowded city, why can't for a residential building to store such amount of hydrogen without a safety distance requirement?
The answer is it would take less time to get it, let's say, accepted than what it used to be, because we have better techniques of risk evaluation or to ensure safety than before. We have, or at least if we apply these advanced approaches based on continuous monitoring and data collection of our process conditions, or at least temperature and pressure would be already useful, but also the degradation of the containment would allow us to fill the gap that we actually have in operational experience. Because as I said, we have a growing technology, and the operational experience comes from experience, I don't know, in the ammonia production, for which we have been using hydrogen for 100 years, but is not exactly the same as considering the storage of hydrogen in a residential area. For instance, we are currently involved in a project, in a European project, on this very aspect, and we are applying some dynamic risk assessment approaches to ensure the safety level in hydrogen storage for a hybrid system for a community, so in a residential area. And we can keep in touch, and I can provide you the results as soon as we get some.
Thank you. Because we have a similar project in Singapore. It's meant for the HDB flat, which is a residential building. So that those seeking some information from overseas, that how such a so-called a safety issue being addressed.
It's very relevant. I think it's a very good idea if we keep in touch then.
Yeah.
Thank you.
Any more questions?
I think we need to wrap up, I think.
Yes.
Yeah. I think it's about time. Per, would you like to wrap up?
Yes, sure. I can do that. Thank you very much to the co-chairs, to Professor Xian and Professor Paulet, for guiding us through this hydrogen webinar. Very good presentations. Very good thanks to Andrew and to Noel for giving an overview of what's happening and what is going to happen, preferably in Singapore and in the region. Great overview from Professor Paulet and from Paltrinieri on the Norwegian side. I think specifically, perhaps, or not specifically, but it's especially the last presentation on the safety and the risk assessment is very useful now moving forward in Singapore as well. As you may know, there are ideas of opening a hydrogen filling station maybe early next year, and together with Singapore Enterprise Singapore, we are organizing a virtual tour to Norway to look at hydrogen filling stations and to discuss the safety and risk assessment around there. So I think all in all, a very good session. This will lead us over to the next session, but before that, I would just say thank you to everybody, and also ask everybody to stay on for the next hour and a half. The next session would be, let me just share this one. It's on the maritime application area related to hydrogen and to hydrogen carriers. We do have two new co-chairs. We have Associate Professor Jasmine Lam, Director of the Maritime Energy and Sustainable Development Center of Excellence at NTNU, Nanyang Technological University. And we have Associate Professor Mehdi Zadeh from the NTNU Marine Technology Center. So Jasmine and Mehdi, are you with us?
Yes.
Great.
Hi, can you hear? Yes.
We can hear you.
Okay.
Yes, yes.
Good.
Hello. Hi, everybody.
Hey,
hello
there as well. So, so with that, I think I would just leave the word over to you, to give a quick introduction and to introduce the next speakers for this second part of the hydrogen webinar.
Sure. Hello, everyone. I'm Jasmine. I'm from Nanyang Technological University in Singapore. I'm very glad to join the webinar, and thank you, Per Christer, for the very nice organization and arrangement for everything. As mentioned, this session is actually part 2 of today's session in terms of hydrogen value chain. Just a few sentences for me, and then later on another co-chair to introduce our speakers. Altogether, we have 5 talks, but really short and brief. Have spent time on the discussion. We will have a panel discussion, and especially focusing on the downstream applications, particularly maritime applications. And I think part 1 is very relevant to set the tone, to set the background for us, and there are many interesting challenges, concerns, and opportunities. So yes, hand over to you, Mehdi.
Yeah. Hello, my name is Mehdi Zadeh, Associate Professor of Hybrid Power System at NTNU Department of Marine Technology in Trondheim, Norway. And as my colleague Jasmine said, we are actually coordinating this session related to maritime applications. And we have 5 presentations in total. We will have Martin Cartwright from DMVGL talking about decarbonization pathway. I myself, Mehdi Zadeh, I will talk in general about the zero emission transportation, maritime transportation solutions, research and development in Norway side. And then I will hand it to my colleague Jasmine talking about low carbon maritime and operations in Singapore. So we will continue with Tomas Tronstad from Norway again, from Hyon, who will give us a talk about the hydrogen developments and fuel cell related applications. And we will end the session with a talk from Sanjay Verma from Wartsila, Singapore, about the clean shipping technology and related developments in Singapore, also considering the port side applications. So I would like to ask Martin Cartwright from DMVGL to start the presentation on decarbonization pathway. The floor is yours, Martin.
Thank you, Mehdi. Let me just check you can all hear me okay quickly.
We can hear you.
Yes.
Good. All right, and now you can see my screen and the presentation.
We can.
Super. Okay. So thanks very much. I'm going to, as I said, Martin Cartwright from DMGL here. I'm going to try the very difficult task now of giving you a quick overview into kind of decarbonisation pathways and DMGL's maritime forecast to 2050. This is quite a big report that we do annually, well received by the maritime industry as a whole. It's very extensive, but let's see what we can do in 10 minutes. To start off, I mean, just to give you a bit of background, as we said, this is about decarbonisation, and eventually the speakers following me today will talk a bit about hydrogen and technologies involved. But it's about the changes that shipping needs to make and is in the process of doing. What this needs is obviously a massive scale up of new technologies and carbon neutral fuels. So all of you will have heard of all the new fuels that are out there. It's an extensive number, but there's no silver bullet, and that's another term you'll hear 100 times over. But the good thing now is, or whether it's good or bad, unknown, but you have regulations and incentives which are taking effect. You have the likes of the IMO greenhouse gas strategy, which have the ambition to halve emissions by 2050. And they will in fact review this again in 2023, so that may be even brought forward. And some of the listeners now might know that the EU has in fact voted to increase their targets for 2030. So society is really pushing for decarbonisation as a whole. So what I'm going to go through now is a bit of what we look into with regards to our maritime forecast to 2050. In the past, we've used 3 different scenarios. Decarbonising shipping by 2040, so that is kind of best case in getting to zero emissions, and another cases are just reaching those IMO ambitions, which is at least 50% reduction in greenhouse gases. And then another scenario in the past was looking at no further decarbonisation, so continuing in our current trend. There's so many things that impact this, but today we're talking predominantly about, or we will be, some of the speakers will be talking predominantly about hydrogen and how this impacts things. And this is the same for our study. It's focused predominantly on fuel, and there's a reason for that. Fuel is the biggest, I guess you could say, saver for greenhouse gas reduction. I think that is obvious. Ships can always become more efficient in how they're ran and how they sail, but fuel is the main factor, and that's the same for everything. It's no different to cars, right? So that's why that is a major focus. So what does this entail? Well, there's a lot of factors, as I've said, but we see large uncertainties, in particular in fuel availability and costs, trade demand, and regulations which make it difficult to make just one or a few scenarios, which is what we've done in the past. So this year we've done 30 different scenarios of what the future may hold. 3 key uncertainties which affect these targets are policy measures. What this includes is the likes of carbon pricing, technical and operational requirements, potential carbon limits, and there's much more there. Another factor is fuel prices, and also naturally the demand. Different fuels are becoming more available, and who's going to use what fuel, and based on how technology develops. So to give you a quick insight, just to give you a base point, this is where the world fleet lies now in terms of current operational vessels running on alternative fuels and those that are currently on order. So still to be built or in the process of being built with alternative fuel in mind, or systems at least. So you'll see currently the existing fleet is less than 1% using alternative fuels, and you'll see there the low values of methanol. LNG is on a considerable rise, and battery systems are now heavily involved. You'll know about some of the ferries and so on in Norway and other parts of the world, and being built here in Singapore, in fact, for a Norwegian owner. But those now in order, LNG sees considerable pickup, and LNG, as I'll go into shortly, is seen as that fuel that can be used now to help with greenhouse gas emissions. But you see a pickup across a few other solutions. But still, there's a lot of work to do, and the margins are still so small. So to take it further, I'm going to give you a quick example of a couple of these scenarios. As I said, we have 30. And so I'm going to take out number 11 here to start off with. As said, we've evaluated the costs of the fuels, the equipment to be installed, the potential retrofitting of vessels in the future when they want to use the likes of hydrogen, ammonia, LNG, and so on, methanol even. And so the figures show an example of transitions taking place in one of the scenarios. You'll see the arrows going between fuel to fuel, which indicates a retrofit, while a shift to the darker colours or share indicate carbon neutral drops in fuel. So perhaps a difficult image to follow, but once you study it, you should understand. But what you can see from scenario 11 here, where IMO ambitions are taken into consideration. You see a massive increase in uptake of LNG in the 2020s. This we're already seeing, and this we can already predict now. We know this is happening. This is an important thing, and this is what's happening in Singapore and in Norway. It's been happening in Norway for quite some time and across the world fleet. And then we kind of see 2030s, a continued uptake of LNG and a rollout of e-ammonia begins. Following that, 2040s, we see an accelerated rollout of e-ammonia, which obviously hydrogen is part of, e-LNG and e-MGO dropping in also. Another scenario we have, which is focused on decarbonisation by 2040, based on low biomass prices, if they were to lower. You see the same as scenario 11, where LNG is still the dominating fuel up in the 2020s. And as you go into the 2030s, you see a rapid transition to biomethanol, which includes, retrofits of vessels naturally. By the 2040s, you see that decarbonisation is complete, and there's a continued transition to biomethanol. Why am I bringing this up? Well, it just shows pathways going forward, depending on how prices develop, availability develops, and the ambitions of IMO and other factors. But what's worth noting next is, if we're just taking an outside perspective and looking at all, as I said, it all comes down to massively fuel flexibility and bridging technologies. We still have a long way to go. And so you can see here, LNG or diesel being the current format in 2020, LNG kind of being that pathway as I've already stated. And then you see the lock-ins from the likes of bio-LNG, hydrogen, synthetic LNG, ammonia, biodiesel, which all have input in time to come as dual fuel combustion engines and alternative fuel ready solutions kind of develop in time. Another kind of indicator of where we are now and how far we need to go. This gives you the red line gives you the current marine fuel consumption, just an average, and then you see the other fuel types. I'll admit, that the base numbers come from a variety of sources and year points, but nevertheless, it still gives the overall indicator of where we lie. With certain fuels not having to change the level of production and availability, LNG is going to be widely available for a long time to come. But you see there on the right hand side, hydrogen is growing, biofuels are growing, ammonia are growing as they slowly become more accessible and available. But we deeply require more of it for it to meet the requirements of the maritime industry. How fast can we make the transition? Impossible to say, but we're going to have to make some changes, and this depends on what influence we have. Again, we've talked about IMO before, but also the requirements of potential charterers and the likes. They have a huge influence on what ship owners and ship managers, or what pathways they take in the future. Currently, what we see, from these studies, I've given you 2 examples, but from the 30 studies, with the forecast 2050, we see carbon neutral ammonia and methanol as the most promising fuels up to 2050. Obviously this is hard to determine. There's in a no carb D scenario, fossil fuels dominate naturally, but when decarb pathways are considered, we see a rapid decline naturally as the phase out fossil fuels. And the most ambitious pathways, decarb, be that decarb 2040, there's no fossil fuels by 2040, and the transition will heavily impact today's shipping. Ammonia and methanol, for now, they offer the best balance of production costs and onboard engine and fuel system costs. The primary energy prices of biomass, renewable electricity and fossil fuels determines which of these are most favourable. If we have large volumes of biomass, for example, available, we expect biomethanol to dominate, while if we have large amounts of renewable electricity or low fossil fuel prices and carbon capture and sequestration, we expect ammonia to be the preferred fuel. And then therefore hydrogen will have to dominate too. carbon neutral MGO and LNG are expected to play a significant role as a transitional fuel, in particular in the decarb 2040 pathway. And they are the main kind of factors in terms of a transition from now to then. In order not to take up too much time, this is just a quick slide to view in terms of an example we have in terms of a bulk carrier in the maritime industry, where we see installing a dual fuel LNG engine and fuel system is the most robust choice today, looking into the future, because of the compliance with regards to 20-25% reduction in tank-to-wake CO2 emissions, according to the current regulations, and it's flexible with regards to the future and retrofitting and drop-in of other fuels. Again, methanol and ammonia requiring retrofit, but it shows the pathways that are available. So another main factor, just to kind of start closing this out, in order to get there with the likes of hydrogen, and as I've said, the speakers following me will tell you more about those solutions. It requires a lot of cohesion across the industry. There's a lot happening today in the maritime industry. There's schemes providing favourable long-term financing to green ships, be it Poseidon principles, if you want to look that up, green bonds, and then there's also risk-sharing mechanisms to reduce the risk for first movers, those that want to take action now and get ready for the future. Again, very important. You can look up Horizon 2020. Regulations to incentivize uptake of new solutions. There's naturally a need for clear and long-term regulatory signals before we can expect any changes to ship technologies and fuels, but these are coming. With IMO making big statements, you can tell that change is needed. And as I've mentioned before, the likes of carbon pricing, performance requirements, perhaps mandatory use of carbon neutral fuels, similar to the fuel sulfur limits we currently have in the shipping industry, standards to measure and compare performance. Well, all these things are a building block for regulations and incentive schemes. Moving on from there, managing decarbonisation risks is of course critical to optimise ships' earning potential and asset value. You know, we can't do anything if we can't afford it. That's just a fact of the industry. So things need to develop and become more cost effective as these technologies develop, which they are. So the important questions always to ask are, how soon will the decarbonisation start? When will carbon neutral fuels be available and at what prices? What does the charterers and financiers require? These are all risks that are critical to optimise ships for their earning potential and value. Well, the highlights. It's been a quick summary to get you in the mood for what the next speakers are going to talk about. But over the next decade, the shipping industry needs to start rolling out the new generation of carbon neutral fuels, hydrogen being high on that agenda. As I've already said, it's hard to identify the clear winners. There's no silver bullet, as I mentioned before, but there are different fuel options across all scenarios, and we see kind of the likes of e-ammonia, blue ammonia, biomethanol, hydrogen in general as the most promising. They've got a lot of space to develop and have a lot of uses in the short term and long term. And we can talk about short sea shipping and deep sea shipping in different regards. Installing dual fuel LNG for now is a robust choice, and we've been saying this for quite some time, and this study shows nothing different. And it prepares you for these fuels I've mentioned in terms of alternative fuels in the future. As I've already said in that last slide just before this one, managing these risks is critical to optimise ships' earning potential. When will they become available? The flexibility, what do charterers and financiers require, and what regulatory parts are imposed, all have a massive impact on how we all do. Okay, that's all from me. If you want to, as I've mentioned, you can always look up this Maritime Forecast 2050 for more information. Just go to eto.dmgl.com/maritime. If you want to chat to me about it or reach out, you can use this QR code here, and I'm happy to guide you in the right direction or give you some more information. And following that, I'll leave it to the next speaker.
Thank you very much, Martin. So we would keep all the questions at the end when we have a panel discussion. But now I would like to go ahead myself, the status presentation on zero emission maritime transport. Yeah, with a good overview from Martin, so I can continue with the research and development part, mainly from Norway side on the zero emission maritime application. So I'm not a hydrogen specialist. So from hydrogen side, I would rely on the excellent presentation from my colleague Professor Poulet from again NTNU. So I am looking at the problem from a general perspective of emission reduction from ship propulsion through electric and hybrid solutions. I mean, of course, with the big involvement of storage systems, batteries, fuel cell, next generation of engines and alternative fuel. So I would I am associate professor at the NTNU Department of Marine Technology, and I am running a research lab on marine electrification at NTNU. So where we are located at the beautiful NTNU, especially in autumn. It looks nice, but maybe not exactly here, but we are actually sitting in the T-Hole campus, which will move soon to the Ocean Space Center, a new, the whole new building and lab infrastructure is a national project thanks to Norwegian government. And what we are doing at the zero emission propulsion side, the focus is on the electrification and hybridization of ship power and propulsion, as I said, for mainly zero emission and autonomous shipping, of course, as the new business of electrification. And we have quite a lot of R&D projects running close collaboration with SINTEF, which is the main research partner to NTNU. So we are running a common hybrid power lab also with SINTEF that I will explain at the end of this presentation. But I mean, more looking at the background of electric and zero emission maritime transport. So as you can see in the picture, a prototype of Yara Birkeland zero emission and autonomous prototype. So the business drives around this field are actually and the first and foremost, we start from energy efficiency, which is the main drive behind fuel and emission reduction, environmental sustainability, and global, national, and international conventions, of course, are helping a lot to get more in this direction, as Martin explained very well. Global increase in maritime transportation, which was again addressed in the overview. Safety and reliability, very well addressed by my colleague Professor Nicola. And as I said, autonomous shipping as a new business and a very important business drive for Norway and maybe for Singapore. So in autonomous vessels, I would say we need an electric heart inside the autonomous ship. I mean, beating quiet and peaceful. So, but what I'm talking about actually as an overview, getting emission reduction step by step. We started from diesel electric drive, which we produce the electricity through the generator cells, and it is a quite established engineering technology. No need to discuss much, but through the hybridization and including battery and gensets to get to feed a common electric and then up to the electric. But then we ended up with the zero emission solutions with the combination of fuel cell and battery. It is still hard for me to imagine a pure fuel cell electric powertrain due to the specific power characteristics of the fuel cell, but we normally can make it happen together with the storage systems like the battery packs. And as you can see, all the way from the diesel oil to zero emission. That's how we establish a hybrid power system. And in the baseline, you can see the hybrid power sources with engine, with fuel cell, with battery, and then they are actually connected through the system interface to a multi-layer control system, which you will have the power management system, energy and emission management, vessel mission management, online and offline optimization layers, and then to the human interface through the cloud, for example. And that makes the structure of the research that we do in the hybrid power system. So from the low level hardware to the high level control and emission management. As I would like to mention a few examples, like the zero emission short sea shipping solutions through pure battery and plug-in hybrid. Well, we have the hybridization through getting the charge from shore to onboard battery, which is of course interesting for Norway because almost all the electric power generated on shore is from hydropower, which is green actually. So we can, easily call it green transportation when we have we are discussing the plug-in solutions from shore. But then how to, for example, charge the onboard batteries and of the efficiency shore to the ship is already a research and development challenge. And as an example of, MF Ampere, which was the ever first pure electric ferry under operation in Sognefjord in Norway since 2015. As you can see, it goes a very short route. I mean, it's half an hour, or even less than half an hour one way. But then still you can save a quite significant amount of CO2, and then getting charged from the two sides just with the 10-minute stop. To the advanced solutions of charging, like for example, the wireless induction charging for electrified ferries, which was again implemented for the first time in Norway by a Wartsila project in collaboration with Tech, which is delivering the charging infrastructure. To the next example, large-scale hybridization and electrification of marine vessels, which, as I mentioned, we do the hybridization with the still use of engines or next generation engines together with the battery, and electrification for autonomy and sustainability, as I mentioned, for mainly autonomous ferries and a very good solution for urban transport. As an example, you can see the NTNU prototype as the first prototype urban water transport through all electric and autonomous ferry. And then again, we have the research challenge of battery charging, power system design, control. Also, considering fuel cell in combination with battery as short sea shipping solution, where we have a fuel cell powertrain, actually from the hydrogen or main fuel up to the electric switchboard. As you can see, the electric powertrain for a typical fuel cell prototype, and examples of some energy management, fuel optimization, and you can distribute quite demanding and fluctuating load profile between the fuel cell and battery, so to get the best of both, actually, to the digital twin and data-driven modeling towards the digitalization of ship power and propulsion. And here I would like to mention an example of collaboration between the academia and the industry as a research-based innovation center, which is called SFI in Norway. And that is a quite consortium of industry and the research partners. And in this case, NTNU is working with SINTEF as the research partner and with a pool of industry towards improve energy efficiency, reduce emission. So we have different sorts of industry collaborators, from design and shipbuilding partners to ship operators to suppliers of the components and equipment. The quite wide range of industry, from Rolls-Royce and Kongsberg to Ward and to the ship operators like Wallenius Wilhelmsen and other partners. So here we have an R&D line of developing low and zero emission solutions, from the feasibility to the ship design, hull and propellers, to power system and fuel optimization, where we test different types of power system topologies, power sources, like again fuel cell and battery, also including to ship system integration, validation, and to the environmental and economic due diligence with the use cases and business studies. As an example of experimental platform, I mentioned in the beginning of my lecture about the hybrid power lab, which is a prototype of a ship power and propulsion. We use a DC power system or DC switchboard to connect the engine gensets with battery at one side and PEM fuel cells on the other side, and then feeding two motor loads, as electric loads, the end user of electric power, although we have quite a small fuel cell package. I mean, 2 packs of 30 kilowatt, but it's still for the sake of demonstration. So here I would like to share with you some examples that I just ran for the students last week. I mean, unfortunately, fuel cell is not involved. It was only the combination of generators and battery. There's still some interesting result on the fuel saving, where we can at the end get some saving by only running the engines in the optimum operational profile, that we call it also peak shaving of the engines. So then these solutions can be also extended to, for example, to fuel cell, hopefully in the near future. Thank you for your attention. I would like to pass the floor to the next presenter, Professor Jasmine.
Thank you. Thank you, Mehdi. All right. Then now is my turn. Let me share my screen. All right. I think you see it. Am I right?
Yes, we do. We see it clearly.
Yes. Okay, so hi everyone. I'm Jasmine Lam. I'm the Center Director of a center which is called Maritime Energy and Sustainable Development Center of Excellence, which is a long name. So in short, we call this center MESD. This center is supported and also funded largely by SMI, that means Singapore Maritime Institute, which is set up by MPA. So that's why we work very closely with SMI and also MPA and of course the industry. And I will be sharing very shortly on options for low time and port operations in Singapore. So just a short overview of the center's vision so that we put in the context, and hopefully there will be discussion on research collaboration. We aim to be a leading global translational research center in maritime energy and sustainable development. That means that's our key focus, and under which, largely speaking, under the umbrella of green ports and green shipping, we include infrastructure, processes, and hovercraft, meaning that it's not just one part of the maritime ecosystem, but we cover actually many different areas. And we have 3 research focuses, including energy management, emission management, and sustainable maritime operations. These 3 are definitely interlinked, and actually most projects involve these 3 areas. And let me talk about the developments in Singapore since IMO GHG strategy. I believe that since the participants are in this session, and you would know IMO GHG strategy, and there are 2 targets, 2030 and 2050, which is medium term and long term to reduce carbon emission or GHG emission drastically. Then on the left-hand side, that means based on that, in Singapore, we do have a national plan. The national plan is to have Singapore being a low-carbon economy and having a low-carbon future. So that means it's not just about maritime, but as a whole, it supports, for example, the Paris Agreement and to deal with carbon emission and GHG in order to solve the issue of climate change. So we can see a lot of different transformations because of that, including industry, economy, society in various aspects. So this is actually one of the reasons why there are so many discussions in various industries, including, for example, buildings and infrastructure, land transport, and sea transport as well. So that's why when it comes to maritime, the very important thing is that within the Singapore area, there is a harbor, and there are so many ships coming in and out. In fact, for those of you who don't know, particularly maybe for the Norwegian delegates, every 2 to 3 minutes, there will be a ship coming in or going out of the port of Singapore. So that's how busy the port is. That's why emission and energy efficiency matter a lot. And on the right-hand side, I summarize the developments, particularly focusing on the maritime aspect. So in Singapore 2 years ago, we launched the Sea Transport Industry Transformation Map. So that means actually Singapore is going through a transformation process in many aspects, not only decarbonization, but also, for example, digitalization. And IMO adopted the initial strategy on reduction of GHG emission from ships in April 2018. And after that, there are so many developments. For example, last year, Singapore launched the new Maritime R&D Roadmap 2030. That means Singapore has got a R&D roadmap, but we renewed it last year. And there are 5 trusts. That means 5 focus areas, and Trust 5 is particularly on sustainable maritime environment and energy. And our center at NTNU particularly focuses on this trust, contributing to, for example, R&D and application works with the industry. And later on, also, the government seeks views on Singapore's long-term low-carbon, low-emissions strategy as well. And then also, very interestingly, MPA, that means the Maritime and Port Authority of Singapore, has announced that next year, okay, that means it's not yet, but it has already confirmed and announced that the Maritime Singapore Decarbonization Blueprint 2050 will be launched next year. So that's why there will be many more exciting things. And yeah, this is what I have told already, that's very heavy shipping traffic. And what's more, Singapore is so small that we have, when we have ship emissions, that's not only about ships and ports, but as a whole, Singapore as a port or maritime city, the residents, those people living here will be affected as well. And also, maybe many of you also know that Singapore is a key bunkering hub. In fact, in terms of sales volume, it's #1 in the world. So that's why in terms of new fuel adoption or any changes in fuel, there will be huge impact on Singapore as a maritime hub and bunkering hub. So here, in our center, we have used, for example, AIS data to analyze the ship trajectories. So this is one of the examples in terms of container ships. So it shows how busy the port is. So you can see that ships are very intense in terms of certain areas, particularly when there are fairways or when, let's say, ships have to berth at particular designated terminals. And also, the next. And how about domestic hovercraft? So that means international ships, definitely, but there are so many hovercraft, meaning, for example, ferries, smaller tugboats. They are also very important in maritime Singapore. So this shows the trajectories within the Singapore territorial water. Also, again, you can see that the emission is very intense. So that's why in the center, it's very relevant that we study alternative energy sources, or actually it includes hydrogen, but also, let's say, LNG, methanol, biofuel, etc. When we analyze energy sources, we focus on the chain approach. That means from generation, for example, feedstock, including the type, availability, usage, production technologies, capacity, cost, and any other concerns. Then to transportation, including storage, logistics, safety, and regulations. So this is very important because we are not just talking about lowering the emission on board. We talk about also, for example, from the life cycle assessment approach, and also how feasible a particular alternative fuel is when it comes to, for example, bunker at Singapore. Because Singapore as a whole, we don't have natural resource. We don't have this kind of fuel, for example, for our own branding or for our own supply. So we must import. So that means in that case, we have to take the supply chain approach. And lastly, application in terms of onboard safety. I think this has been emphasized a lot just now. And also the emission reduction potential and other considerations. And this is an overview of the different alternative energy sources. So since our colleague has mentioned different sources, so I don't think I will highlight too much. But on the left-hand side, those are the short to medium-term measures, more considered short to medium-term. On the right-hand side, those are the options which are longer-term, including hydrogen. But hydrogen can come from different forms as well. So that's why on the right-hand side here, this is more on the renewable energy-based hydrogen. So we see that this is more towards really sustainability, but the technology readiness or the maturity level is not there yet. So that's why R&D is still required. And in our center, we also conduct different types of let's say feasibility or emission reduction potential studies. So this particular chart focuses on or summarizes different types of fuels. And on the left side of this chart, you can see basically we have the current solutions, which is heavy fuel oil, marine gas oil. Then later on, those are the alternative fossil-based fuels. And then here, biofuels. And then this group is non-bio renewable hydrogen. And then we even analyze nuclear and try to compare them. So if you see that the reduction is high, that means the potential is very much better, and it can fit the longer term IMO strategy 2050's targets more. So I'm almost ending the talk. So here are some examples of the R&D projects, and that's why we very much welcome collaborations. We work very closely with our stakeholders. For example, the Maritime and Port Authority. We do have ports, let's say PSA, Jurong Port, our key partners. Shipping community as well. So the key examples, let's say Swire Pacific Offshore, actually DMEGL and other institutes as well. So we have different types of projects, including emission, energy efficiency projects for different aspects, including port, shipping, hovercraft, cargo handling equipment at port, like prime movers. And for today, let's say, because we focus on hydrogen, let's say number 6, this is Hyon. So that means we analyze hydrogen as a source of energy for offshore supply vessel. We do have some projects on hovercraft as well, which is one of the focuses now. And then lastly, this slide somehow to a certain extent summarizes some key efforts to pave the way for low carbon options in Singapore. In Singapore, for both ports, PSA and Jurong ports, they have living labs for green technologies. So meaning that it's not just about research at, let's say, universities or research institutes, but really test bedding. And in fact, decarbonization and digitalization come hand in hand to improve integrated services and efficiency, including energy efficiency. And there is a renewed Maritime Singapore Green Initiative as well to focus on decarbonization. And then also there is a grant call at the moment, but I think just closed in terms of white paper. So that's the development of commercially ready full electric hovercraft, shore-based infrastructure. So that's why there are so many interesting and exciting developments ongoing in Singapore. I think it's very good that Norway and Singapore can collaborate, where then we take reference from each other and decarbonization pathway forward. These are the key references. For those who are interested, I recommend that you may go to our center website, because these reports are having free access, so you can download the full reports. All right, so thank you very much.
Thank you very much.
So next, yeah.
And I would like to pass the floor to the next presenter. So please go ahead, Tomas.
Thank you. You can all hear me, I hope.
Yes.
Excellent. Thank you, and it's a great pleasure to present here among such a lot of great presenters and audiences. Thank you for the opportunity. So I'm going to touch upon hydrogen as seen from a company which is a very much startup company, but which has our roots and our core technology based on 3 extremely strong companies within the hydrogen business. So Hyon is a joint venture company formed by the 3 companies shown at the left side here. Noel, all about hydrogen production and fueling technologies. Hexagon is world-leading composite storage solutions, so that's carbon fiber tanks. And PowerCell, which is a fuel cell provider with world-leading technologies there. And so what Hyon does, very short, is of course to be a one-stop shop for the kind of combined solutions with our owner's product. But in addition, we also add integration and turnkey solutions so that we take the core products and we fit them to maritime use. We are specifically focused on the maritime. And we also add the missing pieces. I'll come back to that. For instance, maritime bunkering stations for hydrogen. Just to give our view on these issues with liquid hydrogen, compressed hydrogen, and other type of synthetic hydrogen-based fuels. Of course, they are all very complementary. One thing I would like to point at, and with all due respect for the very good work done by DNVGL in their big reports and all the work being done there, we think they are missing a few points related to hydrogen. We think we should be all much more optimistic on the hydrogen part. And the one thing which makes this fundamentally clear is that to produce ammonia and other synthetic fuels, you will always produce them from hydrogen. And when we think it's very natural that when you have hydrogen available in this process of making, that you also use hydrogen as it is, a very good fuel, which give the opportunity to use fuel cells, PEM type of fuel cells. So we think there's a missing point in that conclusion from DNVGL. But we will very much like to contribute and work on getting that picture clearer. Then I'd just like to highlight that pressurized hydrogen is actually a very interesting issue, and this is coming up in Norway. We do see very much projects coming where they request pressurized hydrogen. So one example is a cargo vessel being moving goods inland in Norway. This is a tender ongoing now with more than 31 ship owners showing their interest, and the work, the competition is ongoing. So pressure has the lowest capex, the lowest opex, the lowest energy use, and is very highly scalable in its production. Liquid hydrogen, clearly for centralized production. It gives higher energy density, but do have some issues with relate to the capex issue of the equipment and more complexity in storing. What we do is that we can supply integrated hydrogen storage systems. So that means a yard and a designer can really turn to us, and this is important to note to the market, that they have from us and our owners in joint collaboration completely fuel systems designed for their vessels. We can provide the tank storage system, fuel distribution, ventilation, safety system, gas detection, extinguishing, all these issues being solved. And the same thing with fuel cell, we can provide turnkey solutions for the vessels. Going to fuel cells, just to give an example of how the maritime solutions look like. So PowerCell has the world's largest energy density of their fuel cell. They have proprietary technology which makes them more compact and lighter than the competitors that you can compare with. And that includes Nissan, Toyota, these kind of companies. So they have highly interesting technology. So the base unit is a 100 kilowatt size, shown here. And this is being now developed for a 200 kilowatt module, which is this part of the total. This is showing 2 times 200, the complete box here. It has a footprint 2 times 200, which is then 400 kilowatt. It has a footprint of 1.8 times 0.9 meter and a height of 2 meters. So, and the weight is 1100 kilo. And of course, all these things are then put into racks and being implemented in the vessel, very much like we see with the batteries. These systems include all needed balance of plant and even more with the ventilation and cooling systems for external cooling. So very much systems that can be installed in non-hazard areas, and it's running through the NVGL approval as we speak. The way we will implement this typically on cargo vessels will be that we will, in the new buildings, we are talking about new buildings here, we will see a small part of the aft deck being a bit isolated from the rest of the ship and specifically tailored for the storage of both the hydrogen and the fuel cell container. So in this case, we have everything stored above the main deck. You will see this is kind of typically, it could be 20 or 30 or 40 foot ISO containers with hydrogen bottles. This is a standard off-the-shelf product from Hexagon. We will modernize that in the time to come now, but the product as such is already there. You will stack them up like this. You will have a separate fuel cell container like this. And all this is on the aft part of the vessel. It's not taking that much space, and then separated from the cargo and the crew and all these issues. What we see is that doing like this, we have a lot of safety measures. So you will have airlocks for the fuel cell container. The mooring winches will be EX certified. There will be no ignition sources within the hazardous zones, and the vent and inlet and outlets will then be outside of the hazardous zones. The vent inlets will include fire and gas dampers and gas detection. There are physical segregation between the containers with A60 class type. There will be shielding off of the single walled hydrogen pipelines, and of course, as this is on deck, sufficient natural ventilation. And how do you fill this up? You can either kind of lift these containers on and off, but we're also developing now, as we speak, a bunker station. This can typically be placed in any port where you have some hydrogen vessels operating. You will then have the production site being either at the quay or some distance away. Here you will see this is a large plant using the alkaline electrolysis. You will of course also have from Noel PEM type electrolysis available, which is smaller and more compact, more like containerized solutions. But in this case, we are using alkaline, so the production facility is here. This is 1 to 2 ton per 24 hour. You will have some power electronics and some office rooms here, and you will have the compression rooms here. In this case, we have 2 compression rooms. We have full redundancy. So then there will be transport of the gas to the local intermediate storage close to where we bunker. And from that storage, we will feed with no compression and no cooling through the bunker station, being this small container here. In this case, there is a large vessel operating, so we have lifted the container up. It doesn't need to be that, could be other solution as well. But and from the container there will be flexible hoses, and in the interconnection on the vessel there will be breakaway couplings and emergency release couplings according to to the standards used in the maritime. All this is controlled by a separate safety and automation system and uninterrupted power supply. You will of course also be able to offload hydrogen for local transport by truck. And with this system, we have calculated now. We are working on this, but we will be able to bunker up hydrogen. I'll remove this. Sorry. You see this now? Hopefully.
What are you trying to show us, Tomas?
Can you see my slide now?
I can see your slide, yes.
Yeah. So what I was trying to show was that we can bunker up to 3 ton hydrogen in 1 hour.
Yeah, yeah.
In my picture, I had a box in front of this. Sorry for the disturbance.
Okay.
Yeah. Some of the ongoing projects we're working with the industry is we are working specifically on aquaculture vessels. We have an ongoing project called Sea Shuttle, which is a cargo container vessel, a container feeder vessel. We have an ongoing high-speed vessel working with partners called Zero Emission Fast Ferry, ZEF. We have the Heidelberg-Sundberg Fellowship cargo vessel. This is the ongoing tender, and we are part of applications there, and we'll see if we are the lucky winners later in this year. We have our owner Hexagon is working on the Water Go Round project in California, so you will see the Hexagon tanks on the top of the vessel here. This vessel will likely go on stream on water later this year. And we're also working on ferries and aquaculture solutions in projects in the World Heritage Fjords. We will use local power to produce hydrogen for the local ferries and aquaculture equipment. This is just giving a flavor of the things happening from our side, and we look forward to continue the journey with hydrogen. I think that concludes my presentation. Thank you.
Thank you. So the time for the last presentation from Sanjay Verma from Wartsila. So the floor is yours. Please go ahead, Sanjay.
Yes.
Can you guys see my presentation?
Yes.
Yes, we see it. Yeah.
Oh, great. Okay, let me just change it to all right. Thank you. Thank you so much. And yes, it was nice listening to Martin and then Thomas and Jasmine and Mehdi. It was great to hear. And now there are some you may find, okay, this is the driver for the whole change that the industry is going through. And then I'm just, a lot has been talked about hydrogen. And so I'm just using the properties which are really concern for maritime. So, and these are the clean fuel options that we are looking at: natural gas, ammonia, methanol, and hydrogen. So these are the properties, general properties, which everybody is aware of. So I don't need to go. But what I want to highlight here is the supercryogenic part of hydrogen. Then the other thing I want to highlight here is the very low energy value volumetric energy value. So this leads to the space required. Okay, the other thing about safety is the flammability part, which is extremely wide, and that is why it becomes particularly difficult to handle. I'm spending very little time on the slide so that we can have a discussion, or I can give the Singapore perspective and what I see about hydrogen and Singapore. And then the low cryogenic temperature is related to, if we are talking about liquid hydrogen, then we are talking about the storage and complexity it brings for storage. And then this is generally the safety related aspects. So we see it's a cryogenic, it's extremely flammable, it's risk in confined places, and these are the risks, safety risks associated with hydrogen. If we look at hydrogen today, I mean, well, when we look at Norway and when we look at Singapore, we have to look at these differently because it is already highlighted earlier in the presentation, because of your sustainable energy, available sustainable energy to produce green hydrogen. When we look at Singapore, all these, as Jasmine mentioned earlier, these have to be imported. So we don't have a green energy. And even if we prove that, okay, we are using hydrogen, we are not really. If we are producing from hydrogen from a natural gas, then we are not helping the environment in any case. Yeah, if it's not blue or green, then it is not a help anyway. So we have to look at these in a totality, although we may qualify IMO wise, but world at large, we are not doing any justice. So we need to see how we use, what hydrogen do we use, because IMO says, okay, tank to wake, but the world or the globe looks at well to wake. So well to wake is one way, is the right way forward. In Norway, it's justified. If it's produced by natural gas and then used on the crafts. Here in Singapore, it's not justified. I mean, that's the view from the environment point of view. This is not a view from Wartsila point of view. So this is an environmental point of view. Okay, so all this together leads to some conclusion that if we are looking at LNG for 14 days with ammonia, it becomes roughly 8 days. With methanol, it becomes 9.3. If with hydrogen, it becomes 5.3. So short C. And I want to highlight Thomas for his earlier presentation. We all look at shipping in a different way. When he commented on the DNV's report, we all look at the shipping in a different way. We have to look at it holistically. I mean, when we are talking about shipping, we are talking about the ship, which are 85% of the emission and not 10% of the emission. So DNV report, when it is looking at shipping, it is looking at powering the large vessels. So that's where it is, and that is why I want to bring it to Singapore perspective now. As Wartsila, we are committed to 100% hydrogen engines, but where is this 100% hydrogen engines going to go first? We have to remember that only 2.5% of the GHG is being emitted by shipping. The remaining 97.5 on land. Gas is going to be produced, hydrogen as a gas is going to be produced on land. It is the wisest choice to use that hydrogen on land and produce energy and save the environment. So we see that 100% hydrogen engines will be the first takers, will be the land-based, but we are producing these engines. We are producing engines for, whether it is for LNG, it has been produced since I would say 1978 was our first gas diesel engine. So since then we are producing these engines. Methanol, we already have a vessel which is operating, Stena Germanica, which is for last 5 years, it's operating on methanol. Although now we are testing it both as gas as well as liquid in a different engine configuration. So that would be tested within this year. When we are looking at ammonia, yes, we are testing. We have already conducted the first test, and we are going to do some testing later this year as well. And we have projects together with Norwegian customers where we are looking at both fuel cell being powered by ammonia as well as engines being powered by ammonia. Hydrogen, we already have our dual fuel engines which can run in a mixture of 25% hydrogen and 75% natural gas. But we are looking at 100% hydrogen engines, and we would be verifying it. So with hydrogen applications and certain safety systems are to be added. So this is the test where it took place about the mixing of, we mixed in our both dual fuel and single gas engines, and we have gone up to 30%. It can be used on the existing engines without any changes, just with added features of safety. We are going to be testing on both Otto cycle, a lean burn cycle, which will to reduce the NOx emission, but we are also going to test it on the diesel engine in a diesel cycle. So both are under consideration, and we are working on this. Now, because of the time, I have run through it very quickly. Pardon for that. But I wanted to come up with more points when we look at shipping segment. Then hydrogen, whether liquid or compressed, and I totally agree with Thomas here, is compressed is the right choice. But for what? For short sea shipping, for harbor crafts, it's the right choice. We can do that. And Singapore has a lot of these harbor and small vessels. That's where this, along with this coastal shipping, short sea shipping, for deep sea shipping, hydrogen, liquid hydrogen, I think I agree with DNV here, when it is going to come and in what way, whether it is going to come as liquid hydrogen or it is going to come as a hydrogenated fuel, whether it is ammonia or methanol or form of hydrogenated fuel. Well, availability, infrastructure, regulations. Okay, regulations can come faster. In availability and infrastructure in the kind of quantities that we are looking at in the shipping. And when Jasmine talked about bunkering hub, Singapore being a bunkering hub, we are talking about 52 million tons, if I'm not mistaken. That was the bunker last year or in 2019. So we are looking at not 1 or 2 tons of production. We are looking at large scale production and large scale supply chain for this. And that's why I said Singapore perspective, harbor crafts, which are between 250 kilowatt to 2000 kilowatt would be the right choice if hydrogen is to be used. Yes, there are many other alternatives available, but for hydrogen, compressed hydrogen with fuel cell, you could do this. However, I do agree with earlier presentation that only with fuel cell and hydrogen, a propulsion or maritime propulsion cannot take place. It needs a battery support for a proper functionality and the load ramp up of these. With the present, I mean, in future, there may be fuel cells which are very good in taking up load and fluctuating load. But for right now, I think it requires a battery as well. As I said, hydrogen or hydrogenated fuel, both supply chain wise, it is easier as a hydrogenated fuel, whether you convert it into ammonia and transfer it, use it as a hydrogen carrier for your fuel cell, for your other applications, or synthetic methane. Hydrogen combination with fuel cell, this is where the story gets interesting when it comes to hydrogen. Hydrogen as a blend-in fuel, this is with dual fuel. This is what I was talking about. Even today, you could mix 25% and run these same dual fuel LNG engines on these. Concluding, when we talk about Singapore, there has been many activities and initiatives. However, the block here is the operating profile, the expectations of the new and alternate fuels doing the same job as they were doing earlier. So operators' mindset, there is a change in the mindset that is required, and that is the biggest barrier at this moment. Second barrier, as Mehdi also pointed out, was it has to be gradual to be sustainable. Right now, it is conventional. Straight away going electric is not the right way. There is a step of hybridization which makes it sustainable and not totally dependent on funding and support. And that is what is required in Singapore to make it sustainable, stepwise approach. Don't apply one solution for the entire fleet of harbor crafts. Go stepwise, and it will be a successful venture. With that, I would end my presentation. Thank you very much.
Thank you.
Thank you very much. I guess
Thanks
we have
for
a
sharing.
good
Yes.
track of time. Yeah.
All right. So now, after the very interesting talks, we will have a panel discussion. In view of time, we have 14 minutes if we don't want to overrun. Okay, but I think that will be good because that will be a very nice summary and key takeaway. And especially that I would like to ask one question. In the meanwhile, waiting if there is anyone who would like to ask, for example, from through the chat. But what is really key, especially combining from the experience of Singapore and Norway in terms of hydrogen adoption downstream in terms of, for example, maritime, what is really the key? It can include, for example, the opportunities and challenges that you can highlight to us, combining the experience of the two countries. If we are to really adopt it successfully, let's say.
I can interject a little bit. I mean, there's a lot that can be said there. One, it comes down to early adopters and experience. Tomas quite rightly kind of highlighted some projects that are happening in Norway with regards to the ferries and so on and so forth. There's a lot happening there. And even us within DMGL, we're developing regulations in a joint development project called MariSafe, which is about maritime safety of hydrogen. And in developing that, it's about sharing that knowledge with Singapore. Singapore is also now an early adopter in itself. Norway and Singapore have really transcended and are becoming the early adopters of new technologies. In the past, you used to start in Europe and make a transition through Asia. That has made a radical change in very recent years in terms of them both doing it together. So it's sharing that knowledge and making sure both parties share the developments that they have, because Singapore, as we know, is making a big play on hydrogen in general in terms of its future energy source.
Yes. And how about, for example, Tomas and Sanjay? Any views?
Yeah, see, as I said, that Singapore has a lot of small crafts in their harbor, which are targets for these kind of projects. I mean, with compressed hydrogen and fuel cell and a small battery. I think that is the right medicine, I would say, or combination for these kind of, you have pilot launches, you have many small ferries which are going from one side to the other. These are in the range of what Thomas was mentioning, the power ranges that he was talking about, 200, 300, 400 kilowatt power. You can't think about powering a container vessel with a large ocean going container vessel with this. But for these, yes, there is a space where you have to where there is technology available, tested, and that can be brought here and further developed.
Agree. Prof. you would like to say something?
Yeah, I would like to comment on that, and thank you for a very good session and a lot of good comments. I really, of course, agree to what is said about the larger vessels, and I fully agree that the study that GNVGL has made clearly is looking towards the larger vessels. My point is that I think we should not forget the short sea shipping. And you just mentioned, Sanjay, the container vessels, and of course the larger intercontinental container vessels is not subject to hydrogen either. It could be liquid, but I think we will definitely see other things there. What I was referring to is that we have done studies showing that if you look at vessels below 120 meters, that's the area where we think hydrogen in pure form, either liquid or pressurized, will have good options. You will also see ammonia and other things coming there, but these vessel segments is really usable with fuel cells and hydrogen. The power installation could be 1, 2, 2.5 megawatt, and the hydrogen storage would be 2, 3, 4, 5 tons. And you will then typically bunker much more often than we see today. Clearly, you will bunker maybe at each side of the typical distance traveled, and clearly we will be looking for vessels that operate in a fixed pattern in the beginning, so it's easier to set up the infrastructure. But so I'm not in any way contrary to what I think is being said here. Nuance and make it a little bit more. Yeah, make the nuances bigger. Thanks.
Okay. Yeah, thanks for sharing your views. And Per Krista, you would like to say something? Or you would like to have a question?
You're muted.
I'm sorry. Okay, yeah, I'm not sure whether it's a question or a comment or maybe a bit of both. I'm thinking, Jasmine, when you asked what is the what is the driving force or what is the driver for hydrogen development in the different countries and where are the similarities. I think from the Norwegian point of view, it's maybe useful to recognize that the driving force for Norway is not only to deploy decarbonization into the maritime sector. We also have a side interest for being a hydrogen exporter. Basically finding ways to utilize the natural gas resource we have in a more decarbonized way. And by doing that, to build up a market, international market for as offtake of our cleaner natural gas, put it this way, or blue hydrogen, we also have a vested interest in building up technologies that are using this hydrogen abroad. So we have this kind of driving force. It's a dual driving force, and it's a very good cycle, of course. For Singapore, I understand the main driver here is for decarbonization only. But is it also, do you also see the objective of being a promoter or developer of technologies for export? Would you be, would you work with your yards to be helping to develop the hydrogen-based maritime technologies for other markets than yourselves?
I would say yes. Yeah, not exporting hydrogen, but
no,
the technologies.
Obviously.
Yeah, it's like for example, Singapore can be the biggest bunkering hub in the world. Even we don't have any oil, we don't have natural gas.
Right.
That means we don't have such kind of natural resource, but we still can import for example, at the moment, crude oil. Then after the refueling process, still export the products, the petrochemical products. So likewise, now that means the huge impact on Singapore would be then the clean fuels, later on the new fuels. So then which ones that we should make ready, and Singapore should step forward in order to understand and also analyze and also adopt these technologies rather than being just a user. So that's why this is very nice, and also it's nice to hear that Norway will be the exporter. That's one of the driving forces, and actually Singapore is both importer and exporter in various aspects.
We had a discussion yesterday on the CCS, carbon capture and storage in Singapore, and of course the element of hydrogen came in there as well. But do you foresee that there is any way that you would be the producer of blue hydrogen based on the import of whatever, natural gas or crude or other things, and then do the CCS part of that in Singapore? I mean, you have the technology perhaps, but you don't have much of a storage potential. Has that ever been lifted in Singapore?
Anyone would like to answer this question?
Per Krista, we don't have any wells where we can pump the hydrogen back into. Sorry, the carbon dioxide back into. So where are we going to store the captured carbon dioxide?
Actually, that was raised yesterday, and one idea is to export it to surrounding countries that need CO2 for enhanced gas recovery or oil recovery. Indonesia and Malaysia have they are a big demand for CO2 for that, and also a lot of depleted gas fields and aquifers. So the storage potential, but that of course requires an international agreement or regional agreement that you're allowed to export or to dump or whatever you want to call it, CO2 to the surrounding countries.
Yeah, that's right. So that's why, in view of these two countries' experiences, and we do have synergies. I mean, we can complement each other, and that's also the main focus and purpose of today's forum. I think the whole webinar series, Norway and Singapore's research collaboration. So in that case, I think going forward, I suggest that we can deepen the discussion. That means this is not the end, but it's a starting point for the research collaboration discussion. And my slide also, I mentioned that there is an ongoing grant call. There would be more as well in view of Maritime Singapore Decarbonization Roadmap, and I think there would be many opportunities. So that's why I think we should take it from here to discuss further in terms of really some real projects. Okay, it's a nice webinar series, but what's more will be the real actions. Then we can realize those that we want to see in the future. I mean, meeting the targets or fighting climate change and all these. So I think actions are needed.
Yeah, Jasmine, just a remark on the whole the decarbonization part. When we are looking at the decarbonization and we are looking at hydrogen, basically there has been missed a lot of steps on the way. You know, I mean,
a lot of steps are missed.
Meaning there has been, as I mentioned during my presentation very shortly, that straight from conventional to full electric, if you miss out the hybrid step, the adoption becomes very, very difficult. Similarly, between now and the ultimate goal of zero emission or 50% less GHG, there are many steps. So, I mean, hydrogen, knowing about hydrogen, developing hydrogen is fine, but maybe there are more sustainable things in between to do when it comes to decarbonization goal. Hydrogen goal is different. I'm trying to make a difference between decarbonization and hydrogen here.
I think, if I may, just to add on to what Sanjay said, and he's touched upon a very important factor, which I think is important for everyone listening in and the industry as a whole. Hydrogen is very important for our future in terms of decarbonisation, very important. And Thomas, I totally understood your point earlier, and fortunately, I think Sanjay answered it before I even got to answer it. He answered it maybe even better, in fact. And so ultimately, I was talking about volumes. But the worst thing we can possibly do as an industry, and generally speaking, is waiting for the perfect solution. That only takes more time. And so what happens is finding solutions, intermediate solutions to build up to that final gold star is very important. And that's why even, I think, perhaps something you can comment on, Thomas, is yes, short sea shipping is perfect for hydrogen and fuel cells and so on and so forth. But what's also great on the potential coming in is, let's talk about small feeder vessels and peak shaving. We talk a lot about hybrids, battery hybrids. There's no reason why hydrogen can't be part of that hybrid solution for peak shaving, for the likes of feeders, especially in this region where you have a lot of vessels going between Indonesia, Malaysia, Singapore. And these are all intermediate solutions until the bigger picture comes into play, 2040, 2050.
Yeah. A very good point. And
very good point.
Yeah. So sorry, Mehdi, maybe do you wish to have any remark?
No, I had a question related to the hydrogen production, because we had a very good discussion already on the hydrogen storage and usage, but about the hydrogen production, I was wondering in the area of, let's say, electrolyzed hydrogen production, if anyone is aware of any ongoing project either in Norway side or Singapore side.
I think perhaps we can come back to you on that, Mehdi, because we are actually over time.
Yes.
And I have to open another webinar right now. So with that, I'm sorry for breaking off a good discussion, but thank you very much, very much to Mehdi and to Jasmine for hosting this session. Very much to the speakers and for a good discussion. As you said, Jasmine, this is not the end. This is beginning of, I believe, very good collaboration going forward. So with that, I'd like to close this webinar. And thank you all for this session and also the previous session on this very important thing. So I will close the recording, and please, for the speakers, please send me your presentations for distribution if you're okay with that. And I will make sure that both the presentations and the recording of this one will be distributed to the audience. Thank you very much.
Thank you very much.
Thank you.
Thank you all.
Have a good day.